Okay, so last time we talked about random number generation. And today we're going to continue talking about random number generation. And we're going to also talk about a very specific type of random number generation, which is lottery, basically, or leader election. So generally speaking, in random number generation, you want to find a random number R in the range from 0 to m-1. But in lottery or in leader election, the idea is that you have n people, and each one of them wants to be the winner. Each one of them wants to be elected. So in some sense, it's a bit different from just random number generation, right? Because in random number generation, you just want to pick some number randomly. But when it comes to lottery, you actually have incentives. You want to be the one who's chosen, okay? So we will see that that actually changes the problem. So let's just continue with the random number generation. Remember that last time we defined our problem, we said that these are the properties we would like to have. So I want everyone to agree on the final random number R. I want everyone to contribute to it. I want my final random number to be the sum of the contributions of all the people, modulo M, of course. And very importantly, before the generation of this random number, I wanted to make sure that no one has any kind of information about it. And remember that this was mostly based on this idea that if I have even one honest participant who actually gives me a uniform random number, my final R will also be distributed uniformly. And we wanted to also say that no one can tamper with R or its distribution. Now, in the last session, we saw one way of achieving this, and this was using secret sharing. So we used Shamir's secret sharing. This was our final protocol. So we said that every player chooses their own value of Ri at first, and then they send shares of their random value Ri to every other player. And then they commit to it, and then they reveal their commitment. The whole point of using the secret sharing was that some people might not reveal. Right, so we wanted to make sure that if someone fails to reveal, we don't have to reset our protocol, or we don't let them basically tamper with the value of R or its distribution. And then we said that, well, if someone fails to reveal, that's fine because they have already sent shares to everyone else. So other people can come together and they can reconstruct the value of Ri. So even if you decide to be dishonest and not reveal the value of your Ri, the other players will find it, and then we will have the final random number, which is the sum of our Ri's. Okay. But then towards the end of the last session, we got to this point where we basically realized that now we should have the assumption that the majority of our players are honest, right? Because we had this threshold T, and the idea was that any T players can come together and they can basically unmask the value of any other player. They can reconstruct the secrets of the other players. So the number of dishonest players should be less than T, because otherwise my dishonest players might just collude with each other and they can reconstruct the values of everyone else and then they can cheat, right? But then on the other hand, when someone cheats, when someone does not reveal their value of Ri, I want the honest players to be able to come together and reconstruct it. But for that, I need the number of honest players to be at least T. So we talked about how to choose T, and of course, I have to choose T to be basically the majority of my players. Now, this is not something that I particularly like. In this session, I want to get something better than this. I mean, maybe in the particular application that you're implementing, you can assume that the majority of the players are honest. But what if I cannot have that kind of assumption? So again, consider the case of a lottery. In a lottery, when I'm talking about players, each player basically corresponds to one ticket, right? So someone who's rich can just come take part in the lottery, buy, let's say, 60% of all the tickets, right? And then they would violate this assumption. They would actually hold a majority of the players, and of course they can cheat. And we don't want to allow that. So what if I cannot have this assumption? And remember that before, when we were talking about random number generation with deposits, and we said that you have to put down a huge deposit, we didn't actually need this assumption. There, the only assumption was that I have one honest player, right? But my problem was that, of course, the deposits were way too huge. Okay, so let's just try to visualize what's happening. Let's look at the timeline of our protocol and what we would like to see. So this is the timeline of an RNG. I want to say that my protocol starts by people signing up. And let's say they have some time to sign up. And during the sign up phase, they're also choosing their value of RI, right? So I will have some portion of time. And again, my notion of time on the blockchain is not really based on real world time. It's just based on the block number. And by the way, in your smart contracts and homeworks, don't use block timestamp. You should use block numbers, because block timestamps can be changed by the miners. Okay, so coming back here, the timeline of my RNG is like this. First, I have a phase in which the players basically choose their RI, right? And then I have a commitment phase. This is my commitment, where every player is basically announcing to the smart contract the hash of their RI and also a nonce. And then I have a reveal step. So I will have another part here. This is the revelation part, where basically every player is showing their value of RI. And of course, I can have things before this and after this. So at the beginning, I might ask the players to put down some deposits. After the revelation, I might do some extra calculations and so on, but those are not really part of my RNG. So what I care about in my random number generation are these three steps on the blockchain. Now, and of course, again, we have a bunch of deadlines. So let's say that this is T1, it's a block number, which says that you can choose your RI up to block number T1. This is T2, so you can commit between these two block numbers. And then this is T3, which is the last block where you can actually reveal your value. Now, as usual, our problem is that some people might not reveal their value. So when they don't reveal their value, I want to have another phase after this. Ooh, this is a bad color. Okay. Let's say I want to have another phase after this. And this is basically the reconstruction phase. And the idea here is that if someone did not reveal their value, other people should be able to reconstruct the value. Okay. And maybe we also put a deadline on this one. So maybe I say that reconstruction can go until time T4. Okay. So right now, the protocol that I have is using Shamir secret sharing, right? So the idea is that these are the things that are happening off-chain. Sorry, these are the things that are happening on-chain, on the blockchain. And then at the same time, I also said that when the players choose their RIs, off-chain, they're going to send shares. They're going to send the RIJs to other players, right? And this was not on the smart contract. They were using some other communication mechanism. And then the commit and reveal is exactly as it was before. It's just the smart contract checking hashes. And then the reconstruction part was basically, again, Shamir's secret reconstruction. So the idea here was that if someone did not reveal, then the other players could come together and actually create their value of RI. Now, of course, my problem here again was that I needed a majority of the players to be honest. So let's say I want to forget about secret sharing completely. I don't want to use secret sharing. And I don't want to have the assumption that the majority of the players are honest, but I want to have the same timeline. I want to make sure that they can choose their value of RI, they can commit to it, they can reveal it, and I want to make sure that if they don't reveal it, other people can reconstruct the RI. Okay. Now, this looks impossible at first, but this is what's happening in cryptography all the time. So you see problems that look impossible, but then we have solutions for them. So here's the idea. Suppose that when the players choose their value of RI, or when they commit to it, let's say that they also have to give me some extra value. So instead of saying that they can just choose whatever RI they want, let's say that they have to choose the RI, or I don't know, let's call it something else. Let's say they have to choose some value xi, and then I'm going to apply some function to this xi. So I'm going to say my contribution to the random number generation is some function f of the xi. Okay. And then the commitment phase is going to be exactly like before. So I'm going to give my value of RI, well, not the value itself, of course, it's hash, but I'm also going to announce this value of xi. So I'm going to make it public to everyone. I'm going to say, even though you don't know my contribution to the random number generation, which was RI, I'm going to give you the xi that created this RI. Okay. And then the revelation phase is exactly like before. I'm revealing my value of RI. Now, basically, the reconstruction phase is going to be that, well, if I did not reveal my RI, other people are just going to apply the function f to xi, and they're going to get my RI. So others can just compute f of xi. Now, this thing's done because, well, as soon as I give my xi here in the commitment phase, they can already apply the function f, and they can know what my RI is. So it's just like not having the commitment scheme at all. It's like I'm just announcing publicly what my RI is going to be. The way this can actually work is if this function f is hard to compute. Okay, so imagine that the function f takes quite a long time to compute. So for example, I'm announcing this xi here in the commitment phase, but I have chosen this function f such that its computation is so hard that if the other players start computing the value of f of xi, it will already take them all the way into the revelation phase, or maybe even all the way into the reconstruction phase. Okay, so if I somehow have a function f such that computing f is hard and takes this amount of time, which I can basically easily calculate based on my deadlines, right? I can safely give out the value of xi here, and I can be sure that even if the other players are trying to find my value of RI, it's going to take them a long time. So they're not going to see my RI before the time that I want to reveal it myself. But on the other hand, this time that is taken for computing the function f should always finish in the reconstruction phase. And you can do this by just setting the T4 to be much longer, right? So if I have a later deadline for reconstruction, I can make sure that if a player did not reveal here, then the other players can start calculating f of xi for that cheating player at time T3, and they would get it before time T4. Okay, so this is the whole idea. I want to have a function that is hard to compute. But now I have another problem too. Well, actually two problems. My first problem is that this function kind of looks like proof of work, right? It seems like I have some sort of a puzzle, in this case, computing f of xi, and this puzzle is supposed to take a long time. But if you look at it like proof of work, the time that it takes to actually compute f is very much dependent on how much computational power you have. And if I'm doing something like a lottery or a random number generation, I have no idea who the other people are, and I have no idea how much computational power they have. Okay, so that's not going to help me. Instead, I have to somehow create a function f such that the calculation of f cannot be parallelized. I want to make sure that even if you have tons of CPUs and GPUs and whatever, you cannot calculate f any faster. Okay, so this is kind of a different proof of work, and actually we're going to call this a verifiable delay function. So f is a delay function in the sense that it's a function that cannot be computed fast, even if you have a lot of computational power. So the time you need to compute f does not change no matter how many CPUs you have. Okay, you can't parallelize it. So that's our first problem. Our second problem is that suppose someone cheats. So suppose someone does not reveal their value of Ri, and then the other people start calculating the function f, and they successfully calculate it. They find f of xi, which is Ri. Now, they have to give this f of xi to the smart contract, right? Because the smart contract wants to add all of these f of xi's, all of these Ri's, to get the final random number R. But how can the smart contract know that this is not a fake value? So the smart contract has to be able to verify that this is actually f of xi. So this is where we get to the definition of a verifiable delay function. I want this function f to be hard to calculate. I want it to take a long time to compute f, but then I want it to be easy to verify the result of the computation. So if someone gives you xi and f of xi, you should be able to easily verify that this is the correct value. But finding the value should be hard. Now, you can think of this kind of like inverting a hash function, like proof of work, right? So if someone gives you a solution to a proof of work puzzle, you can easily check that this is a correct solution. But actually finding a solution was hard. The main difference here is that in proof of work, if you had more computational power, you could actually solve the problem sooner. But here, I don't have that. I have a function such that no matter how much computational power you have, it's going to take a long time to compute. Okay? Now, I'm going to just give you a paper on Canvas on how you can actually create these kinds of functions. It's much more advanced than the level of this course, but we just want to use them. So I'm going to give you the definition now. So this is what I call a verifiable delay function. A verifiable delay function, or a VDF, let's say with parameter lambda, and this lambda is the hardness. It's going to be a function f such that, so the first constraint is that computing the value of f should be hard. It should take time lambda, no matter how many cores or processors you have. So let's say it takes at least lambda time to calculate or to compute f of any value x given x. Okay. And importantly, again, the difference with proof of work is that this time cannot be reduced by having parallelization. Cannot be reduced by parallelization. Now, again, in the paper that I'm going to give you, there is a more formal and mathematical definition of what it means that parallelization cannot help. But this is all the intuition that we need for our use case. Just that it's a function, and you cannot calculate it any faster if you parallelize it. Now, it's actually kind of easy to come up with a function that only has this one property. If you want a function that cannot be parallelized, imagine if I want to take the hash of x lambda times. So it's like I start with x, I compute the hash of x, then I compute the hash of that value, and then the hash of that value, so on lambda times. There's no way you can parallelize that, because you need each hash in order to get to the next hash. So no matter how much computational power you have, you're not going to be able to compute this function fast. But this is actually not a verifiable delay function because I want my verifiable delay functions to also have this second property. And the second property is given some values x and y. It is easy to verify whether f of x is y. And again, by easy to verify, by easy, I mean that I can do this really fast. I mean that I can do it in very small time. And in our case, I actually also want to reference the gas usage. I want to say that this is a verification that my contract is going to do. So it's not going to use too much gas. It's going to be cheap. Okay, so small gas. Okay. Now I have a better RNG protocol, right? So this is my new RNG protocol. So let's say RNG random number generation based on VDF, verifiable delay functions. Well, I'm just going to mimic this timeline. I'm going to say before time t1, any player can choose their value of xi. And then before time t2, they have to give the hash of ri and ni. Now, here's the thing. The player I should already know f of xi, right? Because we're using it in this hash. We're using ri here. But that's fine, because they can start calculating this and they can start choosing the xi much sooner in advance. They can do it whenever they want. Okay, so here I'm going to assume that there's tons of times before where they could actually choose this. So my first step is that every player, let's say I, chooses xi, and this xi is going to be public, so I'm going to write it in blue, and also computes ri. This is a secret, but we know that ri is f of xi. And ri is a secret in the sense that it takes time to compute ri. So no one else knows ri right now. Only player I knows ri. And then in the second step of my protocol, so before this deadline or between T1 and T2, so between blocks T1 and T2, every player does the commitment. Every player I calls a function on the smart contract. And the function I'm going to call is just the commit function. And I'm going to give it two things. I'm going to give it the hash of my ri. Of course, my hashes always have nonces in them. And I'm also going to give it the value of xi. Okay, so it's now kind of a more complicated commitment, and the smart contract will just save the hash and the xi. Okay. In the next step, I say between times, or let me just write it like this, in blocks from T2 plus 1 to T3, every player must call reveal. Okay. Now, what should the player reveal? They should reveal ri, and they should also reveal their nonce so that the contract can check the hash, right? So this is going to be reveal of ri and ni. But now, what does the contract actually check? So the contract has to check two things now. It has to check that the hash that was committed to was actually correct. So the contract checks that the hash matches. So this is my first check. The hash of Ri and Ni should actually be the hash that was given here. So let's call this one Hi. So this should be the same hash that was claimed in the previous step. But it should also check that Ri is actually the correct value, that Ri is f of xi, that my Ri was actually generated based on the verifiable delay function f. So it also checks that f of xi is Ri. But very importantly, this check was cheap. Because if I know xi and Ri, I can just check whether f of xi is Ri. And this was basically our second property of a verifiable delay function. Okay. Now, the reconstruction part. So after time t3, if some player has not announced anything, so let's say this is step 4. If some player, let's say player I, has failed to reveal, other players can compute the value of Ri. So let's say another player J computes Ri, which is just f of xi. And of course, this happens if the deadline has already passed, if it's after time t3. So if player I has failed to reveal by the deadline, another player J computes this and then gives the result to the smart contract. So, and calls, let's say, I don't know, we can call it reconstruct. Calls a function in the smart contract, which basically gives the value of I and also Ri. Okay. And now the smart contract again does the same check, right? But very importantly, it doesn't do the first check because we don't know. Player I is a cheater. Maybe player I also gave us the wrong hash, right? So in this case, it only does the second check. That's f of xi is actually Ri. Okay, so the smart contract checks that's f of xi is Ri. And then the rest of it is easy. It's just that my random number R is just the sum of all of these random numbers modulo M. Okay, so the last step is that R is the sum of the Ri's modulo M. And the only point here is, again, I'm writing the protocol like this, but when you're writing it as a smart contract, you cannot calculate a whole sum like this in one function. So actually, you have to make sure that your reveal and reconstruct functions keep track of the sum so far. Okay. So this is now my new random number generation. And very importantly, I have to choose the hardness parameter lambda of this verifiable delay function M, such that basically no one can compute F between time t1 to t2, right? So even if I did the commitment at the very beginning here, no one should be able to find my value before the time for commitments are over. Because otherwise that person can actually know my value and they can use it to choose their own value, and we don't want that. But as soon as the commitments are over, everyone has committed to their value. So now it doesn't matter if someone else can find, let's say, player I's value. So I need my lambda to be more than T2 minus T1. So that I'm sure when people are announcing at time T1, no one finds their value until time T2. But I also need to say that if it's the end of the revelation phase, if it's at time T3 and someone has not revealed, others should be able to basically reconstruct before time T4. So lambda should be less than T4 minus T3. Right? So this is what I have about my hardness. It should be more than T2 minus T1, and it should be less than T4 minus T3. And Well, of course, I mean, you can choose all of these parameters. Just choose them in a way that makes sense. Like normally we would just make the reconstruction phase 10 times longer than the commitment phase. It would work. Okay. Now, let's analyze this protocol. The first point is, how many honest participants do I actually need? So you see, I don't have secret reconstruction. Now the situation is that even one player can do all of the reconstruction. So I need only one honest participant. Basically, as long as I have one honest participant, that honest participant is going to give a uniform value of Ri, which makes the entire R uniformly distributed. And also it would stop anyone else from cheating, because if anyone else cheats, my honest participant will reconstruct their value and give it to the smart contract. So now I'm actually back to security even with one honest participant. Okay, which is much better than what I had before. I don't need a majority honesty. Okay, but we have to also talk about incentives, because I'm saying that this function f is quite hard to compute, right? So let's say you're a player here and you see that someone else is cheating. Why would you do the reconstruction? It's going to be expensive. You have to compute the function f, right? And then you have to call this function reconstruct, which will also cause you to pay some gas. So why would I do this? Well, the way I can solve this is by just saying that everyone puts down a deposit at the very beginning of the protocol. And if something like this happens, if player I cheats and player J does the reconstruction, then we take part of the deposit of player I and give it to player J. So we create financial incentives for the players to catch the cheaters. Okay. Now, very importantly, these deposits don't have to be large, because the cost to player J here is just the cost of calculating the function f, and that function f is being calculated off-chain. So you're probably just computing some function on your laptop. I mean, yeah, technically you're paying for some electricity, but that's probably negligible anyway. The bigger cost is the cost of calling this reconstruct function and actually paying for the gas when the smart contract is checking that f of xi is Ri, right? So as long as the deposits are big enough to cover the gas costs, you're fine. And again, normally I would just calculate the cost of gas in the reconstruct function, let's say multiply it by 10, ask everyone to put that much deposits. Okay. Great. But do we now have all of the desired properties that we wanted to have in our random number generation? So actually, let's start from the bottom. No one can hamper with my random number R or its distribution. This is true because if anyone wants to cheat, they have to decide to cheat in the commitments. And in the commitment step, they don't know anything about other people's values. And anyway, the cheating is going to be caught. So it's a stupid thing. No one would actually cheat in this protocol. But even if they do, their value will be reconstructed and it doesn't really tamper with the final value of R. So I have this one. I also have this one. Of course, I have this one by definition. Every player is choosing some Ri, and then my random number is the sum. Everyone agrees on the value because this value is actually computed by a smart contract and it's on the blockchain. Everything in a smart contract is subject to consensus, so everyone agrees with it. But do I have this very first property that was so important for me? Is the value of R chosen uniformly? Does every value have the same probability of being chosen? Not really. Like, at least I don't have a guarantee. right? Because let's go back here and let's see what's happening. So every player is choosing an XI. And I can tell the players, well, if you're an honest player, choose the XI uniformly. And I'm assuming I have one honest player, so that honest player will choose a uniform XI. But XI itself is not really used in the calculation of my final random number. It's f of xi that is added there, right? So even if xi is distributed uniformly, maybe f of xi is not distributed uniformly. I don't have that property here. The property that I have for my verifiable delay functions, the two properties, are only these. So the only guarantees I have is that it's hard to compute f and it's easy to verify the result. But maybe this function f actually changes the distribution. So now this is not really random number generation. It's generating a number that is unpredictable. No one knows what this number is going to be before it's actually calculated. And it's also tamper-proof. No one can tamper with it. But it's not really uniform. Now, here's the technique I'm going to use to make this uniform. I'm going to say every player, instead of just choosing some xi and then setting ri to be f of xi and just contributing one ri, I'm going to ask every player to contribute two different values to the random number generation. So I'm going to say, you choose some xi and you say that ri is f of xi, that's fine. But I say choose another number, choose another r prime I, and choose this one uniformly at random. This is not using the function f. I'm just saying pick a random number between 0 and m minus 1. And then here in the commitment, I'm going to say, give me this second number as well. So this second number is not even secret in any sense. So I don't have to even reveal it because already in the commitment, I told everyone what this value is. Okay, so here, I also say that player I chooses some r prime I, and this is in my range, and this is chosen uniformly. Okay, and when I'm committing, I'm also giving this r prime I. And everything else works normally as before. When I'm doing this final sum, instead of just taking the sum of ri's, I'm going to take the sum of ri's and r primes. Okay, so basically, as a player, your contribution is no longer just f of xi. It's f of xi plus this r prime I that you chose. Okay, now why am I doing this? Because now my contribution as a player I is ri plus r prime I. But if I'm an honest player, r prime I is chosen uniformly at random. So it doesn't matter what the distribution of ri is. Their sum is going to be uniform. Right? On the other hand, of course, I wanted it to also be unpredictable. I wanted other players to have no idea what these values are. And other players can see r prime I, but they cannot find ri because that's the verifiable delay function. So with this very stupid and simple technique, I get all of the properties that I wanted for my random number generation. All the previous properties are still observed there. And right now, I also have a uniform distribution. Okay. So this is how you can generate a random number on the blockchain and be sure that no one can tamper with it and it's uniform and all of those nice things. So this means that if I want to do a lottery, it's very easy, right? I have n players. You just use this random number generation protocol to choose a random number. Instead of setting the random number to be between 0 and m minus 1, you just do it between 0 and n minus 1. So you set n equal to m. And then you say that the random number generated is just the index of the winner of the lottery. Right? But actually, I'm going to show you that lotteries are kind of easier than just random number generation. And this is because of the fundamental difference that we have in a lottery. So if I look at a lottery, I can just think of this as a random number generation game, let's say with n players, and they want to generate a random number basically in the range from 0 to n minus 1. But this random number generation game is actually more general than the lottery that we want to play, because in a lottery, every player also wants to be selected as the final winner, right? So the lottery is not just generating a random number, it's generating a random number plus some incentives. Everyone wants to be chosen. And I can use these incentives to design a different protocol. So plus every player prefers to be chosen. Okay. So to see how we can approach this differently, let's say that I have only 2 players in my lottery. Okay. If I have only 2 players, how can I play a lottery between them? Well, I can just say the lottery is like a commit reveal game, right? So you give 0 or 1. I can just do this. I can say the 2-player lottery is very simple. I would say every player I chooses some value Ri. Chooses Ri, which is either 0 or 1, and then commits to it. Okay, so it does commit of Ri with some nonce. And then in the second step, I say that they reveal their values. So player I calls reveal. Oh, sorry, I forgot to put the hash here. So this is the hash of Ri and Ni. And then calls reveal and gives the values of Ri and Ni. Okay. And at this point, I don't really have the problem of people not revealing, because if someone doesn't reveal, I can just say you have lost the game, right? They want to win. So if someone doesn't reveal, I say the other player has won the lottery, and that's it. So the third step is if a player has not revealed, they lose. Otherwise, I say my R is just R0 plus R1 mod 2. And then R says who has won. Right? So I'm just taking the 2 numbers of the 2 players, looking if the sum is odd or even, and that tells me which player it's. So you see, if I have 2 players, the lottery between 2 players is much simpler than just choosing a random number, because in this case, I have this extra assumption that every player wants to be chosen. And so I can say, if you cheat, I just make sure you lose. And that makes sure that no one cheats, they will all reveal. Okay, great. So now I have to change the formal definition of the properties that I have. It's no longer that every player wins with the same probability, it's that every honest player wins with the same probability, and all the dishonest players just lose. Right? So if someone is dishonest, they're just increasing the probability of their opponent winning. In this case, by not revealing, they're making the probability of their opponent winning literally equal to 1. Okay, so, but this is like only for 2 players. What happens if I have, for example, 4 players? Well, if I have 4 players, I can just create a tournament. I can do something like this. So I can say that player 0 and player 1 do this two-player lottery between themselves, and player 2 and 3 do the same protocol between themselves as well. And of course, all of this is in a smart contract, right? And then the two winners have to again play the same protocol. Okay, so this is actually very much like knockoff tournaments in football, for example. So the idea here is that player 0 and player 1, they both have the same probability of advancing to the next round, right? If they just follow this two-player lottery. And of course, if one of them cheats, the other one will advance. If both of them cheat, we will eliminate both of them, but that's honestly not going to happen. Okay. Now, one of them advances here, the same thing between players 2 and 3, one of them advances up here, and then the winners again play another round. And so as you see, this is much simpler. I don't need any of the things that I had before. I don't need a verifiable delay function. I don't need secret sharing. I can just rely on the incentives. I can rely on the fact that the players want to win. So actually, random number generation is a much harder problem than a lottery. I can solve a lottery by just a sequence of commitment steps. An interesting problem is what happens when the number of players is not a power of 2. So if I have 8 players, of course, I can just have one extra round. I just say play for 3 rounds. But what if I have, for example, 5 players? Or what if I have 7 players? I have some number of players, and that's not a power of 2. So let's do this. Let's say I have players 0, 1, 2, 3, and 4. So I have 5 players. Okay. Now let's say that I want 0 and 1 to play together, and there would be a winner here. Let's call this W1. I say 2 and 3 play together. There's going to be a winner here. I'm going to call that W2. And then maybe I continue creating this tree. I say that W2 plays with 4. And I'm going to call that one W3. And then finally, let's say that this W3 plays with W1. Okay. Now, same rules as before. Anyone who cheats is eliminated. So we can assume that no one is cheating, because if we're assuming everyone is rational, everyone wants to win, get to the top. But here's my problem. The different players actually have different probabilities of winning right now. So player 0 has a probability of half of winning in this first game, and then a probability of half of winning in the second game. So overall, player 0 has 1/4 probability of winning instead of 1/5, right? But on the other hand, if you look at player 2, the probability of player 2 winning is actually 1/8, because it's like half, half, and half. You just multiply that. I want to make sure that everyone has the same probability of winning. How can I do this? Well, it's not actually too hard, right? So here I can say that in this first game, the left player has probability half of winning, and the right player also has the same probability of winning. Okay, so I just assign probabilities to this. But let's look at this game. So the game between the winner of 2 and 3 on the one hand and 4 on the other hand. Okay, so the winner of 2 and 3 represents actually 2 players, but 4 represents only 1 player. So this winner should have twice the probability of winning than this one. So in other words, W2 should become W3 with probability 2/3, and 4 should become W3 with probability 1/3. Okay. Now, again, at this final game, W1 is representing 2 players, but W3 is representing 3 players. Okay, so this one should win with a probability of 2/5, and this one should win with a probability of 3/5. Okay. Generally speaking, if I look at the product of probabilities from every leaf to the root, I should get the same value. I should get 1/5 in this case. And you can check that I am getting 1/5 for each one. And it's actually easy to calculate these probabilities, right? So you just look at every node and you ask how many of the original players does this node represent? So how many of the original players are leaves in the subtree of this node? And that gives you the proportion of probability. Okay. But now I need to be able to go back here and change my two-player lottery so that the players can win with different probabilities. But that's not hard, right? So for example, if I'm playing this game, I want the left player to win with probability 2/5, and I want the right player to win with probability 3/5. So instead of telling the players to choose a random number from two choices, 0 and 1, I say each of them should choose a random number from 5 choices. Okay, so each one of them chooses a random number that is either 0, 1, 2, 3, or 4. And then I just sum these two numbers and I take it modulo 5. And I say if it's one of the first two numbers, so if it's 0 or 1, the left player has won. If it's 2, 3, or 4, the right player has won. So basically, I can just take my two-player lottery and I can make it weighted. I can make it so that one player has a different probability of winning than the other player. And then I can combine these things to create tournaments like this, knockoff tournaments like this, where the probability of winning is different on the different edges.